Yeah. Okay, maybe I will start. So, good afternoon, everyone. Today is our great pleasure to introduce our seminar speaker, the first seminar speaker, Professor Marcel Predovich. Professor Predovich graduated from Stony Brook, and he with the PhD in applied mathematics, and he joined UT Austin first as JT Austin postdoc fellows and research associate, and then he's promoted to assistant professor, and now he's a tenure associate professor in the petroleum engineering department. Professor Fontainebleau has received lots of prestigious awards, including the SPE Formation Evaluation Region Award for the development of the digital rock portals, Texas 10 top faculty, and the Stony Brook 40 under 40 award in 2017. Today, Professor Predovich is going to talk about connecting data, algorithm, and community in digital rock physics. So thank you very much.
Well, thank you very much for the invitation. Hello to everybody from Austin, Texas. Actually from, weirdly enough, in this pandemic time, from my children's bedroom, which is the reason for covering the background with the nice piece of cloth. So this is the world in 2020. So I do welcome a lot of questions. So feel free to interrupt me as I start the talk so that we make this engaging as much as possible. Email me later. My name appears complicated. The good part about it is that if you type it in, even close, I'm the only one who is currently online under that name, so there are benefits to it, so feel free to contact me afterwards. So as Dr. Sun said, I'm going to talk about connecting data, algorithms, and community in specific case of digital rock physics. However, I do want to start the talk, and I'm going to make that point along the line, is that this is not necessarily just about rocks. Rocks is something that I happen to be excited about and study. There's a lot of imaged data that, that basically spurred a lot of data-based simulation. And that part is common to a lot of different materials. Rocks are also porous materials, so there's a lot of advanced materials out there that are porous. So a lot of what I'm going to talk about really translates to different other fields. It's not just about rocks. So without further ado, I would like to introduce rocks and fluids and subsurface simply because I don't expect everybody in the audience to think about rocks or to understand that they have porous structure. So this is going to be really brief, and it's going to kind of just be a slide of visuals to kind of get it down to understand the pore structure of rocks. So this is Barton Creek Greenbelt. It's a favorite place for Austinites to walk around, and you actually see what is a dry creek bed here, Barton Creek. It actually in July flows only underground and not above the ground. So when you zoom in, you actually see this dry creek bed from the neighboring cave. And when you zoom in further, you could actually cut out a piece of core that you want to further study. Now, right now, when you look at it, you think about this as a solid piece. However, it's very porous. You just need a little better vision than my glasses over here to see it. You need X-ray vision. Now, what you see here is a CT scanner, which is in the basement of our department and managed by Dr. DiCarlo, but there's a lot of also microtomography. So this is a scanner that you would see if you went to do a medical CT. It's just adapted for porous media samples. So one part of the adaptation is that you would never really drop a patient vertically into the machine. You actually have them on a bed and move them in, right? So we can go both horizontally and vertically, which is specific for rock samples. There's also microtomography, so that this type of tomography, computed tomography, is three-dimensional, but it gives you images that have a resolution of about 1 millimeter and a fraction of a millimeter. If you go down in resolution, you need much more powerful machine, and you need micro CT, and then you will actually see the details of the pore structure of that core sample that I've shown you. So for instance, inside a sandstone, you will see, this is one slice through a 3D image, you will see individual grains of the original sand that got kind of molded together during the sedimentary rock formation into a sandstone. Okay, which is a hard piece. I have, so this is a three-dimensional rendering. There's quite a bit of algorithms that go from this original tomogram to this processed image that gives you a three-dimensional structure. But this is, whoops, but this is the structure that is ready for further analysis, quantification, and simulation. And it's actually a three-dimensional piece. So what you're looking through here is one slice through it. I also have sort of a 3D visual. So this is a piece of sand that, so this model that you see on the screen enables also 3D printing. And this is, again, a enlarged 3D printed structure of a similar sand. Okay, so that's what's inside the sandstone. Rocks are highly heterogeneous, so we have very different ones. If you look into a limestone, and actually this is actually a piece of chalk. Now you think about chalk as something that you write, or we used to write in schools, but chalk is actually a fine-grained rock that is made of mostly carbonate, and that carbonate is rather soluble. So when water goes through, it will often dissolve pieces called bugs. Okay? So now we get much more heterogeneous structure, but you're looking here at, you're looking at enlarged about 2 millimeters of it, just 2 millimeters, imaged at 3 micron resolution. Okay? And you see something, there's a combination of a fracture and a partial and a dissolution feature, as well as bugs. And actual structure here is porous below the resolution that it's imaged at. So you actually have a multiple scales of porosity. When I actually cut through one portion of this here that involves this bug, I will see a three-dimensional feature. This is the bug. This is now that surface of it. So this is a processed small image of it. And this partial dissolution / fracture is actually in between. There are two planes here that are rather very small aperture apart. Those are my fractures. Okay? So now I'm just looking at whatever scale, whatever imaging, I'm looking at the scale that imaging allows me to look at. Okay? So now, I mentioned rock fluid systems. We have always water and air moving through, and at the scale of petroleum reservoirs, we also have oil, or we might have some certain environmental damage that is close to the surface, so you have lake features within. So you have typically up to 3 fluids competing in those small pore spaces. This is one, again, microtomography image. This is courtesy of Dorothy Wilderschild from Oregon State University. You see air, water, and glass beads in a microtomogram that was on 17 micron resolution. And you see these curved interfaces within this pore space. Okay? Now these fluids easily cut each other off because there's simply not a lot of space, but the space itself is complicated and interconnected as a network. Okay? So this is one view. This is just actually a glass capillary that also tells you the different phases when they, so here you have a triple point of solid and air and water, and at that triple point, they meet at an angle. And that angle also describes or quantifies how are they going to interact on larger scale and what is the type of displacement you're going to see. That's called wettability. And here you have oil. You can see that oil and water have a different contact angle. So those are certain things that we look at when we look at the different fluid phases within pores. Okay. Now here's just a digital, this is actually really old simulation and really old code, but let's see how do fluids displace each other in this pore space, just to give you some idea of what are the certain problems that they look at. So this is the fluid, non-vetting fluid, the fluid that is not preferentially sitting in the rock, is coming from the back through the bug. So it enters through the large pore space. And then you're looking at the color scheme where I meet the other fluid, the one that is resident in the medium, it's red, and the contact with the rock is gray. Okay, so you could see sort of fluid fronts in this fracture a little bit. So this is drainage. This is non-wetting fluid moving in. When that same fluid starts retreating, or the wetting fluid starts coming back, that's called imbibition. And you will see that it proceeds differently, okay? So as it retreats, you might actually trap some of the blobs of the non-wetting fluid inside the pore space. And that trapping is important because it starts blocking the other fluid through flow when it flows. So this, what you see is that it's always different in porous materials. I never go back the same way I went in. And that is the feature of the interconnectivity of the space. Now, we can just look at it and appreciate it. We also want to quantify it, and those are sort of certain upscale parameters that we're interested in. So here at drainage, I can look at the saturation of the wetting fluid, and I plot the curvature that is also capillary pressure across that interface of two fluids. I have to have large pressure to drain, and then that reduces, but you can see that the path here is different, and this is basically the quantification of this residual phase right here. Okay? So there are certain interesting problems that we can always look at rock fluid systems. On a larger scale, way below your feet, and when I say way below, we're going to 3 to 5 to even these days 10 kilometers down underneath. You typically have to have a seal or a trap. You have probably heard the term shale. Those are very tight rocks that both are source rock, the original source rock of the hydrocarbons moving up, but they're also the cap or the trap of a reservoir. So I have to have some sort of structural cap on the reservoir for fluids to collect. But there are reservoirs, whether they're water reservoirs actually or oil reservoirs, they sit in the rocks. So you are saturating rocks. And of course, how these fluids move through the rock is very important. Now, when you think about Grand Canyon, those are some very cool rocks. We can see the entire sedimentary sequence going down to very deep. But they're cool that they're not the reservoir because there's no structural trap to keep the fluids. So there's really empty rocks. All right. So we have introduced the rocks. Now what? How do we actually, so I have already introduced that imaging allows us into the pore structure of those rocks. So I have started organizing this data into a digital rocks portal. And before I start talking about it, I would just like to thank all of the people that have been involved. Original PIs of this project are myself, Dr. Maria Esteva from Texas Advanced Computing Center, short TAC, and Dr. Richard Ketchum, who is in geology department at UT, and also the head of the UT Computing Tomography Facility, UTCT. On the tech side, we have 2 programmers working on it, Andrew McGill and Keith Sermiska. When you submit the data actually has to be curated and reviewed, and Hassan Khan, Javier Santos, Anna Radhakrishnan, and Ankita Singh are working on that. And in the past, we have had a lot of members working on this since 2015, so I'm just acknowledging them all. All right, so we have digital rock petrophysics. I have already introduced all of these multiple images that can happen on multiple scales. And I have introduced CT. So this is CT at millimeter resolution with these 2, then micrometer resolution. You could also have microscopy imaging, which gives a lot of textual information, but it's really 2-dimensional at this point. And you want to integrate these images together with algorithms that work on them to both quantify and to run simulation to get some properties that are of interest. What properties of interest are kind of differs by field. In digital rock petrophysics, we refer to them as porosity, that's the void content, permeability, relative permeability, how fast I can actually, what's my throughput through this rock in terms of flux, and also in the presence of other fluids, capillary pressure that I need to inject or withdraw fluids from my medium versus saturation, formation factor, Young's modulus if I'm looking at the mechanical properties of the solid phase, and so forth. Again, I want you to focus on this not necessarily just through the rocks, but through general porous material properties. But I do need to name what are the properties that I'm typically after, okay? So motivation is that imaging advances provide data sets that really reveal beautiful details of the microstructure. And they allow this first principles investigation using simulation to kind of zoom in and see what's happening. And we have X-ray images, we have MRI images, we have SEM microscopy, focused ion beam microscopy, and so forth. And that results in a lot of image experiments and related simulation data over multiple length scales and heterogeneity, but that is scattered all over different research groups. It is unlikely that the same research group will be the most advanced X-ray imaging research group and SEM research group. So we need to sort of somehow to integrate all of that information. And proper preservation of that data and sharing and collaboration would actually enable what I refer to as data-driven upscaling in simulation. This is not unique to subsurface engineering. So here you see trapped blobs inside a carbonate core that are published on the Digital Rocks portal, but brain tumor is kind of identified the same. It has certain similarities in image processing. So I also get a CT image, and I'm trying to, unfortunately in this case, to recognize where the tumor is. Okay? So in that sense, there's a lot of similarities across different applications of the same imaging tools. And that can happen for material science, biomedical engineering, and so forth. Okay? Now, data loss is actually real. So data storage is typically responsibility of individual investigator and is not necessarily readily accessible to others. And there is actually papers now that point out that 20 years after a paper is published, 80% of the related data is not available anymore. Okay? And that is due to researchers moving and technology transitions. So I will actually exemplify that at one effort where we actually saved the data. I don't know that it was necessarily lost, but exemplifies the technology transition problem. So we wanted to, there's this fracture that I personally used in through my collaboration with Professor Karpin in simulation. And I know that a lot of other people did because she shared it widely. And this was from 2007 from her PhD work. So it's a basically induced fracture in a sandstone. Now, when we went in 2016 to ask, hey, would you be able to post this on Digital Rocks portal? It took 3 months altogether to actually get the data. And it was actually properly stored because it was in a data center. However, the technology changed and it was on tapes. It was basically in a backup, and back and forth took a little over 3 months, okay? Now it's out there and it's been downloaded widely. So these 9 images, so you can see that the average is quite over almost 200 times per image that has been shared. Okay? So this brings me to the Digital Rocks portal. You can go Google it and click on it right now. What you will see is the web interface. We're trying to find what is now emerging as findable, accessible, interoperable, and reusable data principles. There's a lot of push to save the data, and one of it is NSF Harnessing Data Revolution push, which I believe IAIM is actually funded through. And you also have to register your data and make sure that it's what I'm going to refer to as discoverable. I'm going to comment on that a little further down the line. So it's not so easy to find the data even when it's posted online. Okay? Right now, the portal has, since 2015, it started in 2015, and it has collected nearly 120 projects and over 650 users. And there are some different projects here that you see. I would just want you to appreciate the range. There are fractures. Again, these are fractures in real rock samples. In material science, fractures are very real and important. So one would image slightly different porous material, but you would kind of see fractures all the same. There's real experimental 3D velocimetry. This is the only 3D velocimetry image out there that I'm aware of that has been publicly shared. There is particulate straining. I'm going to focus on this a little bit more. This is a CT image. And then there's actually some simulations too. So this is texturally equilibrated materials that are referring to salt, but this is something that would be it is from a natural material or it's trying to mimic the natural material, but would be definitely applicable to material science because there's a number of materials out there that are texturally equilibrated. Okay? And I'm showing here downloads. We're really measuring number of literal downloads on the portal, but that points the data is reused. Okay? Now, say you want to organize a portal. What do you need to do? This paradigm, build it, build something and they shall come, it doesn't really work. You need to actually start by engaging the community. You need to figure out what the scope of the data is, what the sources are, size, types, and structures. What are the data formats? This can bite you a lot. And if anything, right now, the problem that we are having in the reuse of the data on the portal is that everybody's putting up the format that they prefer. Okay? So that results in a sort of a zoo of the type of the data formats that can be out there, and that's not necessarily good for automation. Okay? So we're going to start fixing that and changing it to our internal format, but that's something that you have to think about. You need to organize the data and describe it. You need to figure out what are the typical experimental and simulation workflows and functionalities that users would want to see. What are the licenses for the data? Okay? Because once it's published, it has to be published under license. And if you're not willing to share, well, then you cannot share on a public open data portal. And what is privacy? In rocks, we don't have a problem. Sandstone, you purchase a sandstone, you do an experiment on it, and you move on. You actually typically destroy the core. In the process, if it's in biomedical field, then you have privacy, you have human data, and you have to actually be really careful about that data. So that's something to think about. And as a result, there is a data model, which I'm going to show on the next slide. Now, practical part of building the infrastructure, which is often called a cyber infrastructure, I would argue that you want to let a computing center handle. Otherwise, you have to have in-house specialty for all of it. And most likely than not, you have a scientific domain. I come from the scientific. I want to engage with the data. I want to work with it. I want to simulate. I want to answer questions. I'm not computer, even if I'm well aware about the computer science problems. I'm not a computer scientist myself. So this requires a team, and it's better left to specialists to actually handle the data problems. Computing resources, technology constantly changes, long-term preservation, access to it 24/7, data security, data sharing, all those things. So DRP, I will actually refer to both Digital Rocks Portal and Digital Rock Physics or Petrophysics as DRP. So Digital Rocks Portal provides facilities to manage that. What is the data model? It took us about 6 months to actually talk to everybody and figure out what the data model is. So you figure out, we are organizing data by projects. Projects are sort of an experiments that you run, whether they're simulation or real experiments. And they have a certain descriptor. So each project has descriptors. And there's literally text that describes every project. That's called metadata. Okay? And it's very important because images themselves don't store that. Image is an image. It doesn't store what was your flux of water through that image if it's a water flood that you were imaging. Okay? So that's an associated metadata that you have to somehow record. Now, there's certain physical sample typically involved, or maybe it's artificial sample. Either way, it's still a sample, and it has its own descriptors. And then you have multiple data sets. We are organizing them in whatever is the originating data set. And then there's certain analysis done. So that's sort of a parent-child relationship in terms of data. And then there are also publications that result as type of this work. You do want to relate because they describe this data further, okay? But they're not necessarily part of the data set. So you need research community discussion on this. You need to decide what are the important descriptors. You probably want to leave some of them open. And you also have to understand that some of them will be supplied or make sense for certain projects and some of them don't. And that's a problem of data. So data uniformity is not a given, ever. Now, for a different community, the process would still be the same. The variation of the data model here, I don't think it would actually be all that different. But if I generalize this model further, then I would have trouble with community adoption because nobody would see themselves in the problems that are posted. So technically, I could have said this is digital, any porous media portal, and to a lot of extent it is, but I put rock in there because I want the rock related communities to see themselves in it because that basically enhances adoption. Yeah? And that there's an optimization problem there. But what you want to do is technology transfer is possible, and we could actually, if you give me now a month, month to 2 months, I could figure out how to convert this to a different field. Okay? Now, here's the details that you probably don't want to know about, but I'm going to mention that anyway. What you're seeing when you get to the web page, you see web interface, but that web interface has to supply information from somewhere. And in that case, you need actually a database, both for the metadata, which is quite literally, you can image it as a large spreadsheet that has certain information that is organized based on the data model, but then there's also large storage. These data sets are anywhere from a few megabytes to 250 gigabytes in size. And if I could go and store more, that's a constantly moving target, and they're getting larger and larger. So for that, you need separate storage, and you need the link between all of those. Okay, and that's why you need a computing center that has a parallelized advanced storage. And you want also data. So we are now facing a lot of fires in California. They're very real, and they might burn down an imaging center or any kind of data storage center. So in that sense, you need geographical replication in order to save the data and make sure that you have long-term access to it. So that's why you typically want to let a computing center handle that part. We use all open source software. So there's a architecture that has multiple layers. So this is the web layer. Then there's sort of a business logic. How do I connect web and the databases layer? How do I actually interpret and visualize the data? And then this right now is only partially implemented, but basically how do I connect the data to simulation? That is actually the next step. So how does the portal on one particular case enhance traditional publication? Here's an example of the particulate straining in a carbonate. And this is the metadata that I'm talking about. You have author, collaborators, when is it created, what is the license, and the DOI that enables finding it. Okay? And there's description. That is very important to actually describe what the images are, because images themselves are just a bunch of numbers and they don't have necessarily absolute values of physical properties built within. Okay? So that is the parts that are important. Now we have a project. We have different samples within different data sets and related publications. We have learned that we gotta let the author build the relationships between the data sets, because if you try to impose them, it's not gonna go well. Our initial design had to be scratched, okay? So don't be too rigid. There has to be flexibility to this description. So this is what we call a tree of data set relationships that is shown on the website. Now, after that, you will have certain examples. So this is, in this particular case, we were injecting particulates into core that has an artificial bug within, so we call it a carbonate proxy, but it was really built from sphere packs. And there's flow rates, how fast you're doing it, and what is the concentration of those particulates that are coming in. And that's basically the experimental sequence. So we are organizing our data based on what makes sense for that experiment. For different experiment, you will actually see this is a CT image, a medical CT image. So this is without any particulates, and this is with particulates. So you see larger openings that are there larger than 1 millimeter, so you can actually see them. And you can see that small particulates that are way below the resolution are invading the pore space. And you can see the change in the CT value that can be then scaled, and we can interpret that data. So I know, and there's all of the data information. This data type is just a binary array, So you need a lot of descriptors to be able to read it, and that's part of what we are recording as a user is uploading. Now I know you're dying to know about the VUG effect on this particulate straining. So you can see here before and after particulate flood. So you can see how at the bottom of the VUG you have some particulates filling the VUG, but not in the middle. Most of it is actually, so VUG is actually resisting the particulates, if you will. And you can actually, what we find later is that the penetration into the VUG is way deeper when you have a VUG than if it wouldn't be otherwise. Again, I know you were dying to know. So if you want to know more, there's a related publication on this website that points you to the conclusions of this study, multiple. So in that sense, we are relating both data and publication. All right. So what else are we doing other than just collecting metadata? There's this magic of the action button, okay, which in simple case that is right now actually down, and it will be back up by November, but you can actually give this data set now to a parallel machine to do something with it. And the first case that we actually exploited is just remote visualization. So when you click on that button for three-dimensional data sets, you're going to be connected to a Stampede cluster on Texas Advanced Computing Center, and it's going to tell you, by the way, you're connecting to the supercomputer right now, and that can take a moment because you're establishing that and moving the data to appropriate cluster. And when you do, so I'm just going to really walk through briefly. So you start the session, and I'm going to walk. This is a video built in. So as you are establishing, so when you connect, it opens a remote desktop connection to a parallel cluster, and it moves the data and opens, in this particular case, ParaView visualizer for you. And then you interact with that visualizer the way you would with anything. You need to know how to use it right now, so it's not automated fully. So you need to read the data in from the location that it moved for you. So I'm going to just speed through steps, and you read in the data. Find that, open the file, and you keep clicking through, and then this is now your data is opened. You need to add filters to it in the ParaView workflow to actually visualize what's within. And when you do, you're going to start seeing the end result. You can work with that as if you were on your own computer. Now, in this particular case, so this is a data set of a sand from the portal. It's actually not a large one, so it's not a big deal. This is something that you could have ParaView on your own computer, and you could download the data and work with it on your own computer. However, in case of a large data set, you might not have, if the data set is 50 gigabytes, and my laptop right now has 16 gigabytes of working memory, you can't do that on a laptop. So this is down the line. When we want to explore very large data sets, we have the capability of doing that on a parallel cluster. Okay. Now, there is a certain limitation in experiments versus simulation. So for simulation, we need 3D microstructures. So that's the data input that comes from the portal. And most commonly in the digital rock physics world, you will see single and two-phase flow. And computational power currently limits direct modeling of three-phase flow, complex fluids. I'm going to show this particulate, how far we've gone in particulate flow in a detailed microstructure. So this is introducing particulates that are pretty large, so they get strained and they can block pore spaces, which is essentially what was happening in the experiment that was shown over there. But right now, the experiments really are way ahead of what we can simulate, so we need to catch up. And I'm gonna show right after this a first step in that direction in automation of the simulation that can help us to get there sooner. So a lot of complex processes that have multiple things involved. Either I'm moving a complex fluid through, or I have a process modeling, a particulate invasion, and so forth. They're right now at the frontier of what can be done in simulation, specifically in the detailed simulation and the detailed geometry. Now, how does this compare to other repositories? Most of them actually just post the data sort of as an archived or zipped archive, and then give you a digital object identifier. Okay, so you can reference the data, but data processing and simulation functionality is missing. And there is a benefit in interacting with the data and seeing some visual of it, so you can decide whether that's the data you need in your work. So I don't know, was Wei-Ching, was the poll implemented, or should I just?
I think
ask
go
the
over
users?
it here would be simpler. Yeah, the poll we have. Yeah, we don't have
Okay,
it
so
right now.
well, so we didn't do the poll, but I'd like actually now a little bit of question to you. So there's this digital object identifier that I mentioned. So do you currently, that helps find the data, or so the story goes. And we normally know that papers have digital object identifiers as well. Every time you publish a paper, you get one. So I want to ask you first, do you use Google Scholar profiles or similar to track your or others' papers? And I don't know, does a chat allow us to, can we chat here or see? You have chat, okay? Okay, so
So I just
Dr.
provide my
Sun
answer, for
uses,
example.
yes. So if you can actually post your answer. So, and I wonder how many, what I'm wondering here is that Google Scholar or what have you, it could be ORCID or some other structure. We go to it and it's right now automatically populating papers for us. Frankly, when I need to collect them, I go to Google Scholar and update my CV as I need to. Right? However, have you ever seen a data set automatically found and linked to your profile, whether it's Google Scholar, Web of Science, ORCID, or some other? Okay. So most of the time, most of the people are using some sort of version of automated discovery of papers, and conferences too. Some larger conferences can be easily discovered. In my world, it's American Geophysical Union, but some, again, smaller conferences, not necessarily. But data sets not yet. And that's because of the complexity of the data. There's no uniform format, and finding it on the web is not easy. Now we are connected to as much as we can be connected to in order to enable that discovery. But right now it's quite literally underway. So Google datasets exist since the beginning of this year. There's also a dataset service that basically registers this DOI that we use in the Digital Works portal, but it's not automated just yet. And I'm not going to go into the details how that's done, but I just want to point out that their datasets are coming online, and this expecting to just find them is not going to work very easily at this very moment, but infrastructure is being built. All right. So I am going to now shift slightly to how do we use the data. I am not in itself just interested in data. I really want to use the data for scientific discovery. That's where I'm coming from. So I also want to recognize that in order to be broad in my upscaling of properties, I need multiple data sets coming from multiple research groups, not just from whatever I do. Okay? So in that sense, we need to find a way to streamline and automate this data-based simulation and discovery. So again, I'm going to introduce something that is specific to my world of flow in porous media, but it can be as a problem generalized to anything that depends on multiple scales. And quite frankly, everything depends on multiple scales. Okay? So here I'm going down to micron scale. I could go below. But on micron scale, we have one of those images, and we have seen that it can trap fluids. And the way these fluids block the pore space really informs how the flow through it goes. And the upscaled properties in permeability, relative permeability, and so forth based on it. That in part, so on the flow on the pore scale has very detailed simulation equations that it obeys. I want to upscale those equations to a larger scale. In this particular case, we typically look at a version of Darcy's law, whether it's here equations. I'm cheating. Equations are a single phase and my examples are two phase, but you get what I'm saying. So basically I have this value here of permeability, which measures the throughput, geometrical measure of the throughput through a porous medium for flow. That relates the flux through a larger reservoir depending on this geometrical property, fluid property, mu, and viscosity, that is, and gradient in pressure. Okay? So this is a typical type of relationship on a large scale where I have flux being dependent on the gradient of the driving force, if you will. Excellent. So this is on a larger scale, and I need to find a way from here to here. Now, most generally, when my porous medium is nice and homogeneous and same everywhere, then I can cheat and I can just come up with permeability as a sort of a formula that I can analyze this and upscale really nicely. In the case of rocks, that's not really the case. So I gotta find a way to do it in a more automated way. So I need, this is the whole premise of the digital rock physics, is to provide these permeability data, based on images. So I want to automate that. I want a lot of samples. I want to aggregate the results. The bottleneck is that right now we image much more than we can process. 3D reconstruction and processing is actually a bottleneck, and sharing enough data is a problem. Simulation to get permeability of something like this sandstone right here technically takes on the order of hours, 4 hours, if it's a nice sandstone. The tighter it is, it can take up to 2 days. So we're talking hours to days, just for single phase flow property. I did not introduce two fluids, that takes even longer. So our objective is to automate and speed that up and use artificial intelligence in the process if we can. So we are going to assume that we have the image, and we're going to leverage some computer vision advancements, because computer vision has gone a long way, specifically convolutional neural networks. So what is the advancement that we're going to utilize in this? And I'm going to speed through this simply just to provide you with an idea. So in 2015, imaging algorithms have surpassed human labeling precision, thanks to convolutional neural networks. So if you measure how well an algorithm can recognize an object in an image versus a human, humans won. So this is the error went down and down and down, but it's really in 2015 that went below the human error. Okay? So that is what we want to harness here. However, we also want to do it in a scientific way. I'm measuring fluid properties, physical properties. I also want to make sure that this works correctly. Okay? So convolutional neural networks, I'm just going to wave through them. They capture spatial interactions. They essentially, a filter moves through an image, and in the process captures layers of upscaled data, and somehow encapsulates that information. So this is just given an image, you can do various convolutions of it, and you can actually put a lot of them as an input to your neural network in order to make decisions. So this is roughly how it works through a sphere back image. So you kind of move, as you move this convolution kernel through the image, you get this processed image that identifies features, feature map. And this is, in this particular case, this one identified diagonal edges. Now, this has been applied to flow problems, and the essential idea was, what if I just give it an image? Can I get flow through it, or permeability? So the work started really in 2016, was the first 2D paper about it. It had a lot of errors. Then after that, there was porous media work done, where you input the image and you look for that just permeability, just one number based on the image. That has worked somewhat well. What we're trying to do here is actually predict fluid velocity field. So another image, if you will, based on the image. Now, what we have found is that binary image, just single binary image, and the standard convolutions that you would use in image processing in AI algorithms in processing of photographs fails. You cannot just use an image. You also have to give it a number of filters that are actually not your classical filters from image processing, but are actually dependent on the field of digital rock petrophysics. We know that Euclidean distance to the, for instance, to describe one of them, distance to the solids describes velocity really well. So that's one of those filters that you would naturally use in flow and porous media, but not necessarily elsewhere. So there's a little bit of art in creating the filters that actually work well to actually ultimately get a velocity field. I'm not going to go into a lot of details of deriving these, like what works as a feature that I give to the convolutional neural networks. We borrowed an existing neural network, and this is a bit of we borrowed something that has worked well for recognizing fractures in imagery. So we figured that that has certain features that should work well for us, but we did have to adapt the features that go in. And this topology of the network is, again, a bit of a work of art, and you have to do trial and error to actually get good prediction. However, once we did that, we gave it sphere packs and velocity fields computed on those sphere packs. And those sphere packs were original sphere packs and slightly cemented ones. So the pore space was getting tighter and tighter. And this is somewhat mimicking cementation process that is actually rock formation process. So we figured that should be enough of different data and that the network should learn something from it. And this was done on one GPU that is nothing actually to write home about at this day and age. Okay? And there was 1,000 input samples. We resampled this to 80 cubes because that's what's currently we can push through. This process actually, it did learn something, and we were able to then give it sandstone sample, which is similar structure and porosity. However, the grains are much rougher than a sphere, as well as random set of samples from, well, not necessarily random, those that are well described and have good images on the Digital Rocks portal. Some of them sphere packs, a sphere pack that was not seen. Some of them micro porosity enhanced artificial sphere pack. Some of them limestones, and some of them sands. Okay? All of them, we got really good prediction on these previously unseen samples in terms of permeability. So this is basically Fontainebleau, which is kind of spot on. And these other ones perform rather well as well. This CNN prediction is really on the order of seconds, whereas Lattice-Boltzmann, which we used as a true input here, Lattice-Boltzmann produced velocity. The origin of the algorithm that I'm using for velocity is not really relevant for this study, but it's one that is trusted in Digital Rocks community. So that took anywhere from 4 hours to 2 days. Okay? So we have cut that down and enabled automation. Okay? So CNN was actually successful in using geometric features. We did need domain knowledge to design the features and then predict steady state laminar flow field based on them. And a model trained on sphere packs was able to perform accurately in sort of sandstones and synthetic heterogeneous geometries. All of them were quite well defined as far as image goes, and that's sort of something to think about. And this can enable speeding up detailed simulation and connect different multiple scales. That's something that is coming up in terms of research. There's paper available. There's also a webinar that is entire webinar is just about this simulation that is available on YouTube. You can search for geoscience and geoenergy webinars if you're interested in more. And of course, you can always email me. So in sum, I would like to motivate you to publish your data. It has impact and life on its own once you do. Tools for displaying, interacting with, and simulating data are coming online. This is key for automation because we can connect parallel or high performance computing to the data sets, and that is often necessary. And we can start hosting larger benchmarks for machine and deep learning algorithms. Automation, in my opinion, is key in linking multiple scales, and all of this really translates to different fields. What the workflow that I described is something that could be done in biomedical or material science, which is the material science has a lot of porous materials. Okay? So with that, future vision of this is to start with Portal and then actually do data discovery first with some advanced search right now that is in the process. And can I actually now start interacting with data in the way that we haven't previously pre-designed? So can you just move the data to a remote machine and open Jupyter Notebook and let everybody interact with it with Python? That would be one way. And can I send it to simulation? And then after simulation actually is done, I would like the user to curate that data, approve it, and then it can go back to Digital Rocks portal and it can be published as a new data sets that other people can use. One could also create a database that would now start harvesting. So if all of us here that are in the talk, we go to one data set and resample it in different ways, run whatever simulation is of interest, then there is an upscaled property that can be computed, and all of that could be indexed and put into a database that becomes a searchable database of material properties, and that can be very useful in database upscaling. So that would be cool. All of that requires people in a community and sustainability. So people have to be interested in using it. The entire infrastructure has to be built on how people are already doing research and what is the functionality that they need and use. Okay? And then you can then enable people to kind of jump into a new field much faster if such environment is possible. Now, there's an upcoming visualization and reuse of the data challenge that I invite everybody to participate in. It's actually next week on Thursday. There will be a 3-hour course on visualization, which is really about scientific visualization, but porous materials are challenging in that regard. And then there's actually a challenge with very nice prizes that you don't have to be part of the mini course to participate in. That deadline is on December 1st. This is also on Digital Rocks portal should you want to click on it and find more information and register. Okay. And with that, I thank you. I have gone a little bit longer, so I apologize for that. But I welcome any questions and I acknowledge the funding that went into it.
So, thank you. And thank you, Marsha, for the very inspirational talk, Guy. So I think we would give the time to the audience if they have any questions, and then we can go back to the project PI if they have any questions. So is there any questions from the audience?
So I have a general question. Yeah, so hi, nice to meet you. So I was in UT Austin for 2 years as a postdoc.
Oh, hey.
Yeah. So
the world, this global village is really small.
Yeah. But I was in statistics and data science department. So my background is not really material science or mechanical engineering. So I have a great talk. So I learned a lot. So I have a general question. So studying the rocks. So I'm wondering what's the general applications. For example, it's for the oil exploitation or exploration, or like, I mean, just what kind of application people use?
Anything subsurface. So there is just general scientific questions in rock formation. How did rock form? And typically rocks form over millions of years, right? So how did rock form? How did reservoirs form? And they could be oil reservoirs, but they could be aquifers as well. So if you think about like very basic need in Texas is hot water, right? So there's Edwards Aquifer between around San Antonio and Austin that feeds that basically provides water for over 2 million of people. That water moves through fractures. Did you notice that Barton Creek Greenbelt picture? So there's a lot of limestone and fractured limestone combined with sands and soil, and then some sandstones. So your water and your aquifer lives in those rocks, and how it moves through affects ability to provide water in a big way. What's the way? Do you remember flash floods in Austin?
Yeah.
Why? So topsoil in this area is actually really shallow most of the time, and that's why we don't have basements in Austin for the most part, because you have to break the rock to build one. typically on the order like of 1 foot below the ground, you're going to start hitting the rocks, so you cannot build the basement easily. Because of that, water, when it rains, and it doesn't rain very often, but it rains in a big way when it does, because we have right now hurricane season and hurricane type of rains when it slams into the coast. What we will feel in Austin, which is about, for those uninitiated, it's about 2 hours inwards inside. If you're not on the coast, but if you're central Texas. But those rains will bring a lot of water, and water cannot infiltrate into the soil at the rate that is needed. So it will go where it's easy, it's going to go to fractures. There are not a lot of fractures and creeks and so forth, but that piles up really quickly, and you can have flash floods that affect the way both, and runoffs, that water will escape this region. Okay? So in order to manage that, you need to know, for instance, what is the permeability of that rock.
I see. Okay.
So you can explain. So on an essential level, scientific question is how do fluids flow, move through both top of the surface and subsurface combined.
I see. Okay, great.
And water is very essential to all of us, regardless of. Now, where petroleum engineering just goes way deeper to reservoirs. So all of the questions are the same. They're just in much tighter rock and at much higher temperature, higher pressure conditions. If you went through geothermal energy, which is now, there's a lot of research in that. Again, you are moving, typically enhanced geothermal systems are circulating water/steam through a fractured granite. So again, need to know what is the permeability, so this is just on a larger scale than what I'm talking here, but you still need to know those small scale processes that kind of bite you in a big way if you don't know about them. So that's the upscaling problem in porous materials in general. If I go to material science, the structure of the foam, so all of us have sneakers, and those sneakers have some smart materials within, right? And they're light because it's a solid foam. So everything that I talked about, the pore spaces, you could now look and think about that as a solid space that is interconnected, but relatively small fraction of the volume entirely. And that affects the geometry of that space affects the mechanical properties in a big way.
Okay, I see.
So there's porous media everywhere, you just don't think about it necessarily.
Yeah, so also I'm wondering, like, for example, for this water infiltration process, so it only applies to like materials like rocks. So it's not like, for example, for the metal, there's no really space for the water to like.
Where?
No, I'm just wondering for other kinds of materials, for example, like the metal or all those things.
Metal, no, but metal you would go to small heterogeneities in the metal structure really affect how it fractures. So you still need that small. So imaging in general is used a lot to just see what are the defects in the material.
Yeah, that part. Yeah, I know.
And that can be, a metal, it can be your tooth for that matter, right? So there's a lot of ways where you go with X-ray microtomography to actually just find the defects in the structure of the material. And you would still take that and process the image and then give it as some sort of a mesh to a simulator. It's just the type of simulation and what the simulation do with that input that changes based on the application. So in that sense, the framework is general.
Okay, I see. Thank you.
So we have a few more questions in the chat. Maybe I can just read it out. One
read them out. Yeah.
So one question is that so the convolutional neural network result, are they actually isotropic permeability calculation or actually permeability tensor? How difficult? What is the difficult level change when you talk about the tensor versus the scalar? Right.
So right now we gave it 3D data, and we subsampled that. This is the current hardware imposed limit. We gave it 80 cubes. So those 80 cubes, in terms of relating the pore space structure to should be meaningful. So in our case, they had a few pores across. Now we have found that we actually, if I throw in a fracture through that same medium, it's not going to work as nicely. So we are now working on that.